Take a look. Perhaps it's a witch. Of course not. Witches have brooms. It's her. It's the person. She's on.
In the movie Mary Poppins, two children see a distant outline of a woman falling from the sky, but something about her descent just doesn't add up. Rather than her free fall through the sky frighten her, she seems to be quite content with her very gracious slow motion descent. So what seems to be slowing her fall? Well, in her right hand she is holding an average looking black umbrella. As nothing else about her fall stands out to be a factor, this must be her secret. But could anybody get the same results with the same black umbrella? As Mary Poppins falls from the sky, she holds her very normal umbrella in what seems to slow her acceleration down very drastically. To see this, we need to draw a free body diagram. The forces acting upon her are the force of drag as well as the force of gravity. Because in real life there are many factors that can distort the situation, we need to assume a couple things true. Number one, we need to assume that there is no wind, and number two, we also need to assume that Mary Poppins' mass is 75 kilograms. Now, assuming that she is falling in a positive direction, we can give her an F-net equation of Fg minus Fd. So how do you find the force of drag? Well, there are several different variables that go into this equation, such as the velocity, Cd, which is the coefficient of drag, AF, which is the frontal area, and the air density, which in the equation is known as the Greek letter rho. So how do you put these into an equation? Well, it's CD times rho times V squared times AF all over 2. Assuming that she's been falling for long enough that she has reached her terminal velocity, she will no longer have an acceleration, meaning that her F-net equation will be equal to 0. Because of this, Fg will equal Fd. Now time to sub in the variables for the first equation. The coefficient of drag for the first equation will be equal to 1.42 found off an internet source of a hollow semisphere. The air density of London, where she is falling from, is approximately the same air density at sea level, which is 1.225 kilograms per meter cubed. Her frontal area is the area affected by the drag. This is the area of the umbrella as well as her area. Assuming that her umbrella is the same size as one I found online, of 89 centimeters in diameter, to make calculations easier, we'll make her total frontal area 1. So the variable we are trying to solve for at this point is her velocity. By rearranging the force of drag equation that I showed earlier, we can find the terminal velocity, which is equal to the square root of 2Fg over CD times rho times the frontal area. After subbing in the variables, we can find that the terminal velocity of Mary Poppins' fall is 29.1 meters per second, or in kilometers an hour it is equal to 104.7 kilometers an hour. This insane speed that Mary Poppins would be falling at, equivalent to cars on the highway, is way too fast for her to survive the fall, leaving this part busted. So how much does Mary Poppins' umbrella actually help break her fall? For the second scenario, we are going to drop Mary Poppins without her magical umbrella and see how well she does. Without her umbrella, it will change her drag coefficient to 1.2, as well as her frontal area to 0.378 meters squared. Using the same terminal velocity equation as we used before, we can find her terminal velocity without her umbrella now, which is 51.5 meters per second, or 185.3 kilometers per hour. This means that without her umbrella, she went a substantial 1.8 times faster than she did with her umbrella. So if you were to look outside today and see a woman falling from the sky, what is the minimum size she would need for an umbrella for her to safely fall to the ground? So to find an impact velocity that you could safely land, I asked myself, how high could you jump from? 3 meters would be a height you could jump from and could safely land without injury. For the next part, it is important to note that the force of drag is completely dependent on the velocity. With that being said, there is not just one simple equation you can use to find the velocity at a given time. So a table is created to show how each variable relates to one another. Starting with time, we can make 1/100th of a second increments to show how it will relate with each of the other variables. Area is another constant, so it will not change throughout, as well as the force of gravity, which will also remain the same throughout every calculation. This next part is where it starts to get a little bit complicated, because each of the next variables is dependent on another one. To simplify things, I'll just say that the rest of the variables are given an equation that relates them to one another that will complete each row of data. After all is said and done, if you show the results from the equations, you'll see all the answers at each given time for the distance, the drag, the acceleration, F net, and the velocity. So if you go down to where a person falls approximately 3 meters, you'll see that his velocity at this time is 7.597 meters per second. The data on this table can be more easily seen in this chart, where the x-axis is the time ending at 10 seconds. As you can see, the force of gravity remains the same, and the net force begins to decrease at the same time that the drag force increases. The orange line then shows the total distance traveled, and the red line shows the velocity at the given time. Knowing that 7.6 meters per second is a safe speed to fall at, we can rearrange the drag equation to solve for the frontal area, giving us a result of 14.7 meters squared. This means that the radius of the umbrella will be 2.2 meters. Unfortunately for Mary Poppins, umbrellas just don't come in sizes that large without the classification of a parachute. The disadvantages and abnormality of carrying such a large umbrella significantly outweigh the one and only benefit of having an abnormally large umbrella. And the umbrella in the movie just did not fit the parameters of surviving such a free fall. Therefore, this myth is busted.